is a member of the faculty here at MJC. So she's been teaching math here for quite a while. I forgot to ask like which topics, but I'm sure you'll let us know. One of the things that's wonderful about working at Modesto Junior College, and many other schools don't have this anymore, and that is that you can apply to go on what's called a sabbatical. And a sabbatical is when you get to take a little bit of time off from the teaching and you go out and you kind of reinvigorate yourself with knowledge. You sometimes travel to places that you wouldn't ever get the chance to go, learn about things that you've been fascinated about, and then come back and share them with the community and with your students. And it's a wonderful, invigorating thing to do. And Heidi got to go on the sabbatical where she traveled around Europe, investigating the history of a certain number of mathematicians that she's been fascinated with. So this presentation is the result of her sabbatical work. Heidi has a history of math, and her education comes through Calvin College in Michigan, and CSU Stanislaus, and also Western Michigan University. And she's taught here for a while and is a really dynamic person. I think of Heidi and I think of when I was in the coffee machine room and she'd pop in and she'd have these really cool math t-shirts on. And then she'd be doing pizza and math on Fridays with her students. So a very engaged faculty member, and that's really cool. I was also really lucky to have Heidi as a student of mine. And so I can say that she's quite good, not just at teaching, but I'm an anthropologist. And we went to the Channel Islands of Southern California this last August. Heidi came along as a student. She was the one person who found a really cool artifact at an archaeological site. So yeah, she had the eyes for it. And I really wish I could zoom in and see, because it's this really beautiful green tool. So yeah, so she's not just a mathematician, she's got keen eyes for anthropology too. All right, so let me get this off screen. And then we can welcome Heidi.
Thank you, and thank you for that introduction. I appreciate you guys coming out on a Friday night, and particularly the Friday night of Halloween weekend, right? To come in here and talk about mathematics. That's really cool. I'm a little nervous about the time because I am speaking about infinity, and that's a really big topic. And I've got less than an hour, so I will do the best that I can. So my title is Beyond Infinity, The Life and Work of Georg Cantor. And as Susan shared with us, this comes from a sabbatical that I took this spring. And this was one of the mathematicians that stood out to me. But my topic went out in the advertising under two different titles. One of them was this title that you see here, but another was Mathematics, a Human Endeavor. But honestly, that's what I'm talking about. I'm going to be talking about Georg Cantor and his life and some of the struggles that he went through and the amazing mathematics that he came up with. But before I get to Cantor, I'm going to spend a little bit of time talking about my travels and just giving you little snippets of some of the other mathematicians that I studied. History is a big topic. Mathematics is a big topic. I had to narrow it down. So I spent my time in Northern Europe, and I was looking at the history of mathematics from the Renaissance to the present. And you see the map here. This is where I traveled. I started up in Edinburgh, and then my last stop was Halle, Germany, which is where Cantor lived and taught. One of the reasons that I really like to present mathematics as a human endeavor, and what I try to do is to put a human face on mathematics for my students, is that I think, not just I think, 30 years of experience in teaching tells me that many people, if not most people, see mathematics as some kind of stone monolith that has existed since the beginning of time. And there are some people that are just born able to climb over this monolith, and other people just smack into it and beat their heads into it and can't get further than that. But really, mathematics is something that human beings have developed either because they were interested in it or because there was a need for what it is that they were doing and what it is that they were developing. So starting back in the 1500s, towards the beginning of the time period I was looking at, we have John Napier. John Napier's story is that he was born into nobility. He was the 8th Laird Merchiston, and so he didn't do mathematics as a job. For him, mathematics was a hobby. And he is the person who developed logarithms. And at that time, that was a huge advance in how quickly we could calculate things. And it was very helpful to astronomers and navigators in order to have this. And in fact, other mathematicians said of Napier that he had doubled the life of the astronomer because they were able to get so much more done because they were able to calculate so much more quickly. What you see over here on the right is a tower that remains of the castle that he lived in. And what you see down here in the middle of the slide is an early calculating device. It's known as Napier's rods or Napier's bones. And these were used for many hundreds of years after Napier invented them. And in fact, Isaac Newton used this, and he promoted the use of Napier's bones and said that it would help people to be able to calculate more quickly. Speaking of Sir Isaac Newton, he was born into somewhat different circumstances than Napier. His family did have land, but they were by no means aristocracy or nobility. His father died 3 months before he was born. And when he was 3 years old, his mother remarried, and she left him behind with his grandmother, which he always resented her for, and he did not like his stepfather at all. Eventually, his mother was widowed again, and she really wanted Newton to come back and farm the land. Well, Newton wanted to go on to school. His mother had the money to pay for him to go to school, but she wouldn't do it because she wanted him to be a farmer. So Newton actually was a valet for other students and worked his way through Cambridge until he got to a point where he was able to get a scholarship. And we know Newton today as one of the greatest mathematicians and scientists of all time, who was one of the inventors of calculus and came up with equations of gravity. And speaking of gravity, so this is his house. He was born, well, actually right there in that room. And this is a view out his window, and this tree is the apple tree that he said inspired him in terms of the theory of gravity. So continuing, we have Carl Friedrich Gauss, again, very different life situation. He was born into a poor working class family. His mother was illiterate. She did not remember what day he was born on. He didn't know when his birthday was. She remembered that he was born on a Wednesday, and it was 9 days before the Feast of Ascension. So when he grew up, he became a mathematician, and he was working on the calendar, particularly with dates for Easter. And later in life, he was able to use the information about having been born on a Wednesday 9 days before the Feast of the Ascension, and he was able to work out when his own birthday was. He was a mathematical prodigy when he was about 3 years old. He was standing next to his father, who was working on some calculations for his business. And Gauss, who was 3 years old, noticed that his father had made an error in his mathematics, even though Gauss had no mathematical training. So his skills with mathematics became known, and the Duke of Brunswick decided to sponsor him and help him to get his education. Gauss became, well, we always like to rate things, right? Even mathematicians, we will rate the top mathematicians of all time. Gauss always comes out in the top 3 along with Newton and Archimedes. So, really wonderful that this Duke of Brunswick sponsored him and allowed him to go on and get his education. So far we've seen men. We've only seen male mathematicians. And one of the reasons for that is that women were not allowed to go to university at this time. But there were some women who persevered and who found a way. And I find their stories quite inspiring. I gave a talk last month about overcoming obstacles and women of 19th century mathematics. So Mary Fairfax Somerville was born in Burnt Island, Scotland, which is just north of Edinburgh, across the Firth of Forth. And she was always intrigued with the natural world. She lived, there was a beach nearby that had tide pools. She would go out and watch the birds. At night, she'd look out her window at the stars, and she was quite intrigued by the natural world. When she was 13 years old, a friend of hers invited her to come over and look at some fine stitchery work that she had been doing. And while Mary was at her friend's house, she saw a women's fashion magazine, and there was a little mathematical riddle in there, and it just had numbers, but then she turned the page and she saw X and Y. And she said to her friend, well, what is this? And her friend said, oh, that's algebra, but I don't know anything about it. I just know that it's algebra. And so Mary went home. She read through the books in her family's home, and she couldn't find anything that told her what algebra was. She knew no one in her family would be either willing or able to help her, because at this time it was thought that if women studied something so difficult and abstract as mathematics or science, that they would probably go crazy. In fact, she tried to do a little bit with mathematics, and her father said to her mother, we need to put a stop to that or we'll soon have Mary in a straitjacket. Remember that guy who was working on the longitude who went stark raving mad, right? So anyway, I need to keep moving so that I can get to Cantor, who is who I'm going to talk most about tonight. But eventually, Mary got married. Her husband died after only about 2 or 3 years. So at that point, she was independent and respectable. She had some money of her own. She was able to purchase some books on mathematics and study it and learn about it. And she actually advanced so far that she had papers published by the British Royal Society. And she even came to be known as the Queen of the Sciences in the 1800s. So, yet another story, Ada Byron Lovelace. That name Byron is probably familiar. She's the only legitimate child of the poet Lord Byron. But Lord Byron left Ada's mother when she was an infant, and Ada never knew her father. And Ada's story is a little different too. All of these people have their own story, very, very different stories. So Ada was born into the nobility, but never knew her father. Most women were not allowed to study mathematics and science. Ada was forced to, because her mother did not want Ada to turn out like her crazy, philandering, womanizing father. And her mother felt that poetry was what kind of led him to that. So her mother actually had Mary Somerville tutor Ada, and their families became quite close. Ada's work, she worked with Charles Babbage on his difference engine, and she actually had a bigger vision for it than he did. He was thinking of it as just a calculating device, and she really had a vision for it as a computer that could do many things, such as composing music. And eventually her work inspired Alan Turing, who worked on the Enigma code, worked in Bletchley Park during World War II to break the German Enigma code. And the mathematical work goes on. So, Sir Andrew Wiles and Sir Roger Penrose are a couple more that come to mind that I came across during my travels. This is in Oxford at the Mathematical Institute there. Sir Andrew Wiles was inspired to go into mathematics when he was 10 years, as a 10-year-old. He found a math puzzle in a book. It's called Fermat's Last Theorem. It's a very simple theorem to state. I'll just say it's something like the Pythagorean theorem. It's kind of like a squared plus b squared equals c squared. But it was a problem that had been around for 350 years and no one had solved it. And he decided as a 10-year-old he was going to solve it. It was one of those things that was easy to understand but hard to prove. And in the 1990s he did, hence Sir Andrew Wiles. And also you'll notice that the building here at the Mathematical Institute is named after him. Roger Penrose was also inspired to go into mathematics through playfulness. In an interview, he shared that his father had no boundary between his work and his play, and his father had a woodworking shed out in the back of the house, and he would make puzzles and games out there. So there are lots of different ways that people get inspired to go into mathematics. Newton was interested in the movement of the planets, and that's why he developed the calculus. On the other hand, we have Wiles and Penrose who were inspired by playfulness. So anyway, if you're interested in more stories like these, I did keep a blog while I was traveling, and I'll give the address for that at the end of the talk. But now we need to move on to my last destination, which was Halle, Germany, which is where Cantor lived and taught. So I just want to point out a few features of Halle. This is the Marketkirche, or the Marienkirche, the Market Church, or the Church of St. Mary. This is the Red Tower. So this city is called the City of the Five Towers. And the statue here in the middle is of George Friedrich Handel, the composer, who was born in Halle. And Halle is not very far away from Wittenberg, where Martin Luther pounded the 95 Theses into the church door and started the Protestant Reformation. And he preached at this church a number of times, and his death mask is there and casts of his hands and so on. So it's quite associated with Luther. So before my travels, I did a tremendous amount of reading of books and articles and research on the internet and so on, but there were some things that I just couldn't find the answer to before I left. So I sent out emails to mathematicians in Europe. I did not know them. I just did some research online and looked for universities where I was going. And one person that I was in contact with was Dr. Manfred Stern, who is pictured here. And I simply had one single question. I wrote and I said, is the Nerven clinic where Cantor was hospitalized, is that still standing? He wrote me back the very next day. He said, "Dear Heidi, thank you so much for your email. I would love to meet with you while you're here." When I got there, I found out that he had cleared his calendar, told the people he worked for that he was going to be hosting an American colleague for a week, and absolutely graciously hosted me for a week. So I want to dedicate this talk to him and say thank you to him. He got me into places that I would have never been able to get into on my own. He got me into Cantor's former classroom, where he also taught. This is the classroom, and Manfred taught there himself. And coincidentally, today is Manfred's 70th birthday. So Manfred, happy birthday, and thank you. So, launching into the mathematics and into the talk about Cantor. Before talking about his life, I want to give you a little mathematical brain teaser. I'd like you to think about the counting numbers, 1, 2, 3, 4, etc. No negatives, no fractions, right? Just think about the counting numbers. They go on, they're infinite. Okay? What I'd like you to do is to compare those with the even numbers, which is also an infinite set of numbers. So if we were to compare those in terms of size, what do you think? When I look at the even numbers, there seem to be some gaps there. It seems like some things are missing. In fact, if you take the counting numbers and you want to get the evens, you have to throw away half the counting numbers, don't you? You have to throw away the odds. So, is infinity just infinity? Are these sets the same size? Or could it be that one is twice as big as the other? Okay, so just something to think about as I tell you a little bit more about Cantor. Cantor was born in St. Petersburg, Russia. When he was 11 years old, his family moved to Germany. His father was a wealthy businessman, and he was later a stockbroker in St. Petersburg. But his father suffered from poor health, and they needed to get away from those harsh, cold winters in St. Petersburg. So they moved to Germany. He comes from a family of artists and musicians. In fact, there were some very famous musicians in his family. His grandfather was a soloist for the Imperial Orchestra in Russia, and his grandfather's brother was the director of the Vienna Conservatory. And Cantor himself was an excellent violinist in his younger years. Also, they were a very religious family. Cantor was baptized and raised Lutheran, and his father really instilled the faith into his children. Cantor discovered early on an interest in mathematics. He was quite good at mathematics, and so we'll see how that played a role in his life. Before I talk further about him, I need to share a letter that his father sent to him or gave to him on the day that he was confirmed into the Lutheran Church. So I'm going to have 3 slides in a row that have quite a bit of text to them, but Cantor's relationship with his father and Cantor's faith life really impacted his work tremendously. So I think this is an important thing to share in order to lay the groundwork for our talk about Cantor's life. So again, this was a letter his father wrote at the time of his confirmation into the Lutheran Church. So it's kind of a letter of, hey son, I'm proud of you, and here's what I see for your future, and this is what I'd like to see in your life, that sort of a thing. So it starts out, "Dearest Georg, through the goodness of the Almighty Creator of the universe and the Father of all living creatures, May this day be of blessed influence upon your entire future life. This sure heart which must live in us is a truly religious spirit which keeps and maintains us throughout our entire life in that silent, undoubting communion with our Heavenly Father. But in order to prevent as well all those other hardships and difficulties which inevitably rise against us through jealousy and slander of open or secret enemies, one needs above all to acquire the greatest amount possible of the most basic, diverse technical knowledge and skills which are absolutely necessary if the industrious man does not want to see himself pushed aside by his enemies and forced to stand at the second or third rank. Your father, or rather your parents, and all other members of your family, both in Germany and in Russia and in Denmark, have their eyes on you as the eldest and expect you to be nothing less than a Theodor Schaefer and, God willing, later perhaps a shining star on the horizon of science. May God give you strength, persistence, health, sound character, and his best blessings, and therefore you should follow only his ways. Amen. Your father. No pressure, right? The whole entire family in Germany, Russia, Denmark, they all have their eyes on you as the oldest to become a shining star in science. Theodor Schaefer was a teacher of Cantor, so he needed to be at least as great as his teacher and perhaps a shining star on the horizon of science. When his father says science, what he had in mind was the practical sciences, particularly engineering. And looking back to that last one as well, his father, it's interesting. I'm going to spoil a little bit right now and give a little bit away. Cantor's work was so groundbreaking that he did end up having a lot of enemies. And he also ended up struggling with mental illness, with depression later on in his life. And it's kind of interesting how his father's letter almost touches on all of these things that he's going to be dealing with. So he's talking here about open and secret enemies and how Cantor really needs to study. He needs to be prepared in order to protect himself against all these enemies. And you know, that we want to see him be a shining star, and that where his strength is going to come from for all of this is from God. So Cantor's study, when he was a teenager, he was at Darmstädter Gewerbeschule, which is a trade school. So again, possibly his father really wanted him to go to engineering. He found that he really had a love for math, though. So he plucked up his courage and he wrote a letter to his father, and he expressed that he would really like to go into mathematics, that was really attracting his attention. And his father wrote back and said, okay, you know, go ahead and do that. And Cantor wrote back and said, dear Papa, you can't imagine how happy your letter has made me. My sense of duty and my sense of my own desires have been fighting within me, and I'm so happy to know that this will not distress you if I pursue my own feelings. So he very strongly wanted to go into mathematics. He said it was the heart and soul of him to be able to do that. He went on to study at the Polytechnicum in Zurich. And then he came back to Germany and studied at the University of Berlin, which was a top-tier school for mathematics. He studied under some very famous mathematicians of the time, Kronecker, Kummer, and Weierstrass. This is actually a picture of Göttingen, also a top-tier school in Germany for mathematics. Spent a semester there, but he finished his PhD in Berlin, and his dissertation was on number theory. So I've given you a bit about his life, but now we're going to go back to that math puzzle that I had you thinking about. Are there more counting numbers and fewer even numbers, or are the sets the same size? And I use the term size a little bit casually here, but are they the same size because they're infinite? And before we really tackle that, we need to get a little bit of terminology down and get a little bit of an idea of set theory. So here I have pictured 3 different sets. S, the set of shapes, M, the set of some mathematical operations, L, the set of some letters. And if I were to ask you which of these are the same size, a very easy way to approach that question is just say, well, up there on the top I see 1, 2, 3, 4 things. The set in the middle, I see 1, 2, 3 things, and the set on the bottom, I see 1, 2, 3, 4 things. So set S and set L are of the same size. And the way we indicate the size of a set, it looks like using an absolute value symbol. This is called the cardinality. So the cardinality of set S is 4. The cardinality of set M is 3. So we can see that the cardinality of S and the cardinality of L are the same. They're the same size because they have the same number of elements. Well, there's actually an even more primitive way to do this. And we need something that's more basic because these we can count. But you can't count all the numbers. You'd never be done, right? Because the set is infinite. So another way that we can do this is to consider a one-to-one correspondence. There's one thing in the set L for each thing in the set S, and there's one element in the set S for each element in the set L. Therefore, there's a one-to-one correspondence. This is kind of the key to the whole argument. So take a look at that and make sure you understand what I'm saying about that. If you're able to match everything one-to-one from one set to the other, then you have the same amount of elements in each of the sets. So let's go back to the natural numbers and the even numbers represented by N and E, natural and even. Well, I can draw those arrows in there, but do they really match up one-to-one? Well, isn't it true that for every counting number, every natural number I have up there in that top set, that if I double it, I get an even number? Is there any natural number that you have that you're not allowed to double it? Like once we get to 1,000,000, you can't go times 2 anymore? No, for every natural number, you're going to have a double. And we can go back the other way as well. For every even number, you can cut it in half, right? So the cardinality of N is equal to the cardinality of E. In other words, there are the same amount of even numbers as there are natural numbers, even though it seems like there might be only half as many. Okay, and by the way, since I do have such a short period of time in order to talk about such a huge topic, I'm just going to give something away right now and just give you some information. If you can take a set and you can find an element to start with, and you can list the rest of the elements, you can make a list of them so that they can be counted off, it is the case that that set has the same size or the same cardinality as the counting numbers. And what I should have said is if you can take an infinite set and have a place to start and then list them in order and you can count them off, then they have the same cardinality. They can be matched up to the counting numbers. So let's consider another set a second. This is the set of the integers. Those are represented by Z, and the Z comes from the German word for number. Well, I said a minute ago that if you could start somewhere and list these things and count them off, then they would be of the same size as the set of counting numbers. But I see dots on both ends here, the right-hand side and the left-hand side. So in some sense, it's infinite in both directions. So maybe this is twice as big as the counting numbers, because I see all the counting numbers starting right here and going on up, but then we have as many more of them down here in the negatives, plus we've got that 0. So what number would we start with? Because there is no smallest one. Well, Cantor gave us a very clever solution to this. He basically took that set and he folded it in half, and he interspersed the negative numbers with the positive numbers. So starting with 0, you got -1, +1, -2, +2, -3, etc. You're not going to miss any of the numbers all the way down. And now we can line those up with the natural numbers. And I'll just mention to you, if you want to think about this a little bit, I think you can pretty easily find a rule for matching. Actually, you kind of have to find 2 rules. You need to consider the negatives separately from the ones that aren't negative and see how you could match them to those other numbers below. Okay, it basically has to do with doubling and adding 1 or multiplying by -2. So it is the case that the integers and the natural numbers are also of the same cardinality. They are sets of the same size, same level of infinity. So your next brain teaser, and then I'll talk about Cantor some more. Okay. What about the positive rational numbers? And rational has that word ratio in there. So what I mean by that are, what about all the positive fractions? And that set has the name Q for quotient, right? Which is the answer to a division problem. So what about the positive fractions? And I just want to focus our attention for a moment on the fractions between 0 and 1. So you've got a half, but I can put a fourth in there and an eighth in there, and can't I keep cutting that unit in half forever? So I've got infinitely many fractions just going a half, a fourth, an eighth, a 16th, a 32nd, a 64. We could just keep going that way. And I haven't even touched fractions like 2/3 or like 9/10. There are infinitely many fractions just in between 0 and 1. So if we continue the rest of the positive side of the number line, I've got infinitely many fractions in here, and in fact between any two whole numbers. So what do you think? Do we have more fractions than we do counting numbers? Or is infinity just infinity and it's the same because they're both infinite, right? So I'll let that rattle around in your head a little bit while I talk about Cantor some more. So anyway, the questions that I just asked are going to come up on the screen. So reiterating, are there more positive rational numbers than counting numbers? But some things to think about. Is there a smallest fraction that we can start with? Remember I said we had to start somewhere and be able to list things? And even if we can find a smallest one somehow, what would be the next fraction right in a row after that one? Okay, so this could be pretty challenging. After Cantor finished his PhD at Berlin, where he did his dissertation on number theory, he taught for a brief period of time at a girls' school in Berlin, and then when there was an opening, when there was an appointment at Halle, he took that. So this is Halle Wittenberg University. This is the building that he taught in. This is the main hall of the university. See the lion there? They have lions flanking the steps on either side. It's very regal. This is looking towards his classroom building, which is called the Melanchthonianum. Melanchthonianum. So here's his classroom. It's of course been updated since his time, but that's the space in which he taught. Okay, and that's the view from the front. So here Cantor is in Halle, and his sister introduced him to a friend of hers, and her name was Valley Gutmann. And later that same year, Cantor and Valley were married on August 9th of 1874. And so this is the marriage banns in the register at the church. After I came home, I made contact with Petra Cune, who did a little more research for me and found this information and sent the pictures on to me of the registry. We also have a registry of the baptism of their first child, Elizabeth Marie Johanna, who was born in 1875, and then also a list here of the godparents for Elizabeth, whom the family name knew as Elsa. I was looking into his association with the church and whether or not he was a member there, and we'll see a little bit more about that later on. But this, again, is that market church that I was mentioning earlier, where Martin Luther had preached and where Handel was baptized and where he learned how to play the organ. This is Martin Luther, by the way. It's a little plaque to him out in the front. And here's one of the organs in the church. Oh, another famous name associated with this. Once this organ was installed, Bach, Johann Sebastian Bach, came and gave a review of the organ, and his son became an organist at this church. There's a lot of history here. Another view of the organ, and then this is the baptismal font where their daughter was baptized, and also where George Friedrich Handel had been baptized as well. So part of why I'm bringing up so much of his faith is because it's something that gave him the strength to do what he did mathematically, because he was going against, in the study of infinity that he did, he was going against not just the current trends or decades worth of a different viewpoint, or even centuries, but millennia worth of a different viewpoint to infinity. No less a thinker than Aristotle said there is no actual infinity. And what Cantor was saying is, I'm going to grab all of the whole numbers or all the counting numbers, and I'm going to think about that whole thing as a set, as a complete set. And people up to that time had thought about infinity more as like a verb than as a noun. It's something you keep moving toward, right? You can keep progressing toward it, but you never get there. And he said, no, I'm going to grab the whole thing. We're going to talk about the whole thing. Gauss, we spoke about a little bit earlier, he said, I protest against the use of infinite magnitude as something which is completed, which is never permissible in mathematics. Infinity is merely a way of speaking. Remember, I mentioned this is one of the 3 greatest mathematicians of all time, saying that this is never permissible to speak of infinity as something that's completed. And then someone else that we know quite well, Galileo, he did a little bit of exploration into the infinite, but his conclusion was that the difficulties in the study of the infinite arise because we attempt with our finite minds to discuss the infinite, assigning to it those properties which we give to the finite and limited, but this is wrong, for we cannot speak of infinite quantities as being the one greater and the one less than the other. So he was up against centuries and millennia of this idea that infinity is not something that you can think of as a whole completed thing. But I love Cantor's thought on this. The essence of mathematics lies in its freedom. Don't tell me what I can't do. The essence of mathematics lies in its freedom. We can go beyond the boundaries. We can go beyond the borders. So let's do that. I had you start thinking about the fractions. So I'm going to see if we can do some sort of listing. And you'll see that I have up there 1 over 1, 1 over 2, etc. You might be questioning me on the 1 over 1, but that is a positive rational number. It's a ratio. You can take any whole number and put a 1 underneath it. Well, okay, if I start counting these off, that's great, except that where is 2/3? Because all of these have a 1 on the top, and I'm just counting along the bottom. Well, okay, how about if I make another row and I put everything with 2 on the top down there, then the next one everything with 3 on the top down there. But so first of all, I'd like you to look at this matrix and think about whether or not every fraction is on there. Could you find 19 300ths? Is that going to be here somewhere? Right? Can't you just go down to the 19th row and the 300th column and it's going to be there? Because in the first row I have all the fractions that have a 1 on top. Second row, all the fractions that have a 2 on top. Okay, so as I'm doing the rows here, as I'm writing out the rows, I'm using 1, 2, 3, 4, 5, all the way down. But then as you look at the columns, that first column is all the fractions that have a 1 on the bottom. Then the second column, all the fractions that have a 2 on the bottom. So in that way, I do have all the fractions. But they're in a matrix, they're not in a list. Well, here too, Cantor got clever. He decided to make a zigzagging path that would go through this list and catch all the numbers. So he's going to zigzag. He's going to come in at 1 over 1, go across, zigzag down, go down, zigzag back up, and here's what that looks like. So he's created a path. We could just number that off. That's a little hard to see. You can follow it with your eyes a little bit. It's kind of like going through a maze. You could think of those arrows as being a string threading all of these fractions together, and if you pulled that string, you could pull them into a straight line. And I attempted to do that, but I don't know that that's so helpful, so I actually created it. And I put a string through all of them, and I pulled on the string. So let's see what that looks like. And what you're watching for in just a second is how these, as I pull the string, those are just going to follow right along and they're going to straighten out. Okay, so here it goes. Okay, so we're going to be able to get this entire array of fractions to line up, and then we can count. Oh, that went too far, too fast. I gave away too much. Okay, since we have a starting place and we have a logical way of arranging these, we can count them off using the counting numbers. Therefore, even though you've got infinitely many fractions between 0 and 1, infinitely many fractions between 1 and 2, infinitely, you know, et cetera, et cetera, et cetera. We've got basically infinity times infinity fractions. It's still the same level of infinity. We call this countable, by the way, simply because you can line them up with the counting numbers. So this is known as being countable. Therefore, the cardinalities are the same. And you might say to me, yeah, but how would you ever come up with a formula that would match those up or give you those numbers? Well, I'm going to put it up here really quickly. There is one. And this is being videotaped. So if you want to watch it later and pause right here and check that out, you can. But I'm going to move on to the next slide. Okay? So this monument is in Halle, dedicated to Cantor. Actually, it's a big cube, and there's a dedication to a different person on each side, and I just didn't even think to take pictures of the other people. So I don't know who's on the other sides, because I was so interested in Cantor. But check this out over here, these little circles. I don't know if you can see it, but there are arrows connecting the circles. So this monument includes the demonstration that we just looked at. And that demonstration is that the rational numbers are countable. And there is a quote down here that you probably can't see very well, but it's Das Wesen der Mathematik liegt in ihrer Freiheit. The essence of mathematics lies in its freedom. So that quote is actually on this monument to Cantor. Okay, so prior to the time of Cantor, the idea of infinity was that it was something you just keep going. Things could grow without bound. They could keep getting bigger and bigger. Cantor was looking at these sets as actual infinity or completed infinity, and he actually gave that a number. It's called a transfinite number. And the number he used was Aleph null. Aleph is the first letter of the Hebrew alphabet. And so if you want to talk about how many numbers there are, how many counting numbers there are, the amount of counting numbers that there are is Aleph null. Okay? So in some sense it's a different way of saying infinity, but being really specific about it. So summary. What we've seen so far is that the number of all the sets we've looked at, the natural numbers, the even numbers, the integers, and the rationals, all have a size or a cardinality of Aleph null. So something to think about is, does this mean that all infinite sets have the same number of elements? Is infinity just infinity? Okay. We're going to consider one more set, and that's the real numbers, which means all the points on the number line. And you might be thinking, well, didn't we already do this? Didn't you just do that with all the fractions? Well, here's the deal with fractions. If you have a fraction, let's keep it simple. Think about the fraction 1/2 and imagine how you would write that as a decimal number. It's 0.5. It stops. 1/2 is 0.5, the end. Or think about the fraction 1/3. It's 0.333333, right? It keeps going, but it's the same thing all the way down. I think if you ponder this a little bit, you'll realize you know about some numbers that don't do that. In fact, one of them we use quite a lot in our math classes, and that's pi, right? 3.1415926. Another one, if you've taken a couple years of algebra, you'll know about E, the Euler number, which has to do with compound interest and so on. And if you're an artist, maybe you know about this number, which is called phi or phi, P-H-I, and that's 1.6180339. That's known as the golden number. So again, the question is, all right, so if we throw all those numbers on the number line, including all those decimals that don't repeat and don't stop, do we get a higher level of infinity then? And just an FYI, the real number line is also known as the continuum. So if I use that word continuum, I'm talking about the real number line. Okay. So backing away from the math again for a second, looking some more at Cantor's life. Cantor was a very social person. He was very well regarded. This picture here is at the University of Leipzig, and there was a group there of mathematicians that would get together for coffee, and often the mathematicians from Halle would join them, and Cantor was part of that. And Cantor was described by members of that group as being very witty and having sparkling conversation. He always wanted to be the center of the conversation, but that was okay because he was just incredibly entertaining. He was also known as someone who was very generous. He was always helpful to someone in need, just a really interesting and kind person. People also enjoyed getting together at his house. He had this house built. He actually, professors, especially when they were first starting out, did not make much money at all. In fact, when he started, he was what was called a private docent, which means, yes, you have permission to teach, and by the way, just whatever the students pay you is what you get, right? The university didn't pay them. But his father had passed away by this time, and he had an inheritance which allowed him to care for his family and have this house built. But there was another side to his personality as well. Cantor was, I'd go so far as to say, hypersensitive to criticism. And because of his work in particular, there were people that were, holding back and saying, I don't think we can go there. And particularly, one of his former teachers from Berlin, the University of Berlin, Leopold Kronecker. In fact, Kronecker kept some of Cantor's papers out of Krell's journal, and Cantor was very upset and very hurt by that. But even something, for instance, when there was an opening at Halle University, Cantor was asked to draw up a list of some mathematicians that could perhaps fill that opening. And one name that he put on the list was Richard Dedekind, who was a friend of his, and Dedekind turned down the position, and that was that. There was no more correspondence between Cantor and Dedekind. I mean, if you offended him, that was just, he sort of closed the door on that. And I could tell some other stories about that, but I'm watching my time, so I better keep moving on. But for as much as with his colleagues, he needed to be the center of attention, and he needed to be the one sort of driving the conversation. When he was at home, now this picture is taken later, but this is Cantor and his wife and their daughters and a son-in-law. But even when the family was younger, Cantor would be happy to have his children leading the conversation. And every evening after dinner, he would look over at his wife and say, "Are you pleased with me today? And do you love me?" Which I thought was just very sweet. So at home, he was just quiet and allowing his family to run the conversation, and he always checked with his wife, "Are you pleased with me today? And do you love me?" And I think part of the way he was with his colleagues sort of did come from a sense of duty to his father. And since his father had wanted him to do something else but gave him permission to be a mathematician, I think he felt a lot of pressure to really prove himself. So I think that was part of it. In 1884, he went to Paris to meet with some colleagues. He met with some big-name mathematicians there, Poincaré and Hermite. Many of the mathematicians were out of town. This was early in the year in 1884. So Cantor got to indulge his love of art and music. And we do know that he visited museums, perhaps the Louvre. We know that he definitely went to the Paris Opera and indulged his love of music. But 8 days after he arrived in Paris, he was called back to Germany because of some sort of emergency in his extended family, and we don't know anything about what that was. If it was a health issue, financial issue, we don't know what that was. In March, he had his 39th birthday, and then suddenly he had a mental breakdown, absolute mental collapse. He was hospitalized for about a month, and it was terribly shocking to him and to his family. His oldest daughter was 9 years old, and there are writings that talk about how bewildered she was about the change in her father. And Cantor himself was very shaken by this. So even though it only took him a month to recover, he was quite a changed person. And Cantor looked back on this episode and thought, I let Kronecker get to me too much. I let the irritation with Kronecker just get inside and bother me too much. So he wrote to Kronecker later that year to make things up with him and to kind of be friendly with him again. And he felt that he was probably too focused on his mathematics. So he began to diversify his interests to kind of balance his life. And he became interested in many, many things: study of scripture, Rosicrucianism, literature, the plays of Shakespeare, and whether or not Shakespeare actually wrote them, Or if Francis Bacon wrote the plays of Shakespeare, so he took on interests like this to try to just keep his life a little more balanced and not so intensely focused on mathematics. But so now I'm going to do something kind of dangerous and focus you back on mathematics. Okay, so hang in there, hang in there. Okay, so talking about the real numbers, the whole number line, I'm going to focus us down on even just a narrower section of that and just consider the real numbers between 0 and 1, all the decimal numbers between 0 and 1. And as I've shared, if we can line them up and count them off, then we've got the same level of infinity as we do when we're talking about the counting numbers. So I'm going to present you with a list. I, of course, can't fit the whole thing on this slide, but I've listed as many as I can. Dot, dot, dot at the back, because these things keep going. I've got some rational numbers in here, and I've got some irrational numbers in here. And this is going to keep going down below. And I claim that I have a list, and I can count them off. But then I realize I left a number off the list. And that's this number. And I know it's missing, even on all the other pages of paper that I've written these all down on, all infinitely many of these things. Well, this number isn't the number that's top on my list because the first digit of this number is different from the first digit of this number. And when I look at the second number, the second digit is different from this second digit. So it's not the second number on my list. And then when I go to the third number, I've made sure that this number is different. In fact, can you see what I'm doing to make sure that they're different? In each case, I added 1 to this digit to create the number down here. So I go one more, that's a 0, I added 1 to get a 1. So I'm making sure that as I go, this number does not match the first number in the first place, the second number in the second place, the third number in the third place, all the way. And we keep going in that manner. And you might look at this and say, whoa, that number down here, that sure looks a whole lot like this number up here, except I made sure that in the 8th place, they didn't match. So this number wasn't on the list anywhere. And you might say to me, well, okay, just put that number on the list and then it's all good. But I can just do the same thing all over again. In fact, I can do that same thing all over again forever and ever and ever. And I'm never going to run out of numbers that are actually missing from the list. And I know that was pretty fast. If you stick around for some questions afterwards, we can talk further, or I can give you some good suggestions of books where you can look this up. But it is the case, and this, by the way, this is Cantor's famous diagonalization proof. It is the case that all the points on the number line, in fact, just the points between 0 and 1, just the decimal numbers between 0 and 1, form a greater level of infinity than all the counting numbers. Just the decimal numbers between 0 and 1 are more than all the fractions on the whole number line. Okay? So we actually do have different sizes of infinity. I mentioned that the number line is called the continuum. Well, Cantor called the number of items on the number line C. So we have aleph null, which is how many counting numbers we have, and then we have C, which is the cardinality of the real numbers, or the cardinality of the continuum. And we actually know a relationship between these two values. If you take aleph null and you use it as an exponent on the number 2, that's exactly equal to the number of points on the whole number line, which is exactly equal to the number of points just in between 0 and 1. So if your mind isn't blown, maybe you're tired because it's a Friday night and you're not listening closely enough, because this should be pretty mind-blowing stuff. In fact, there are so many more irrational numbers, which we hardly work with, right? You guys work with counting numbers all the time, negative numbers all the time, fractions all the time. You've seen pi and maybe another couple irrational numbers. But it is the case that if you were to be able to throw a dart at the target of the number line between 0 and 1, your probability of hitting one of those numbers you're familiar with, like a half, 3/4, 2/3, your probability is 0. And your probability of hitting an irrational number, which we're less familiar with, is 1. Okay, you are certain to hit something irrational. That's how much bigger this level of infinity is. So what Cantor became interested in was enumerating different levels of infinity. There are more levels of infinity other than just those two. There are bigger levels of infinity. And what he was really curious about was whether or not the very next level of infinity, Aleph 1, after Aleph 2, is actually equal to the infinity of the continuum or not. This is known as the continuum hypothesis. And again, I think I'll have to wait and say more about that afterwards if you have questions. It turns out, I'm just going to say this, it turns out that that's an impossible problem. And that's probably one of the things that he also struggled with. As we look back at his mental breakdown and more that occurred later in his life, it's probably the case that he was bipolar. That's what current scholarship shows. The records from his hospitalizations still exist, and they have been studied and continue to be studied. There were mathematicians who really accepted his work. One was David Hilbert, who said, "No one shall expel us from the paradise that Cantor has created." And another was Bertrand Russell, who said, "Cantor is one of the greatest intellects of the 19th century." But most of the sentiment was more along these lines. This is Leopold Kronecker, his former teacher and mentor. Kronecker says, "Cantor is a scientific charlatan, a renegade, a corrupter of youth." Henri Poincaré, who was also a very renowned mathematician, said Cantor's set theory and transfinite numbers are a grave mathematical malady, a perverse pathological illness that will one day be cured. Them's fighting words, okay? Cantor's a teacher. Imagine being a teacher and being called a corrupter of the youth. Imagine your teacher and mentor calling you a charlatan. And imagine your work being called a disease. Okay, this is heavy stuff. So this is one place in which he found refuge in the strength of his faith. He actually saw his work as being in some sense dictated to him by God, and that he was just a scribe. So that allowed him to see his work as having importance, and it also kind of took some of the pressure off of himself. He wrote to a friend, "My theory stands as firm as a rock. Every arrow directed against it will quickly return to its archer. How do I know this? Because I have studied it from all sides for many years, because I have examined all objections which have ever been made against the infinite numbers, and above all, because I have followed its roots, so to speak, to the first infallible cause of all created things." The first infallible cause of all created things. Interestingly, at this time, there was an encyclical that was put out by Pope Leo XIII that was intended to bring faith and reason into fruitful discussion. And there was a theologian at this time by the name of Countable, who, prior to reading Cantor's work, had been talking about the actual infinite with regard to God, and some other theologians were opposed to his work. But when Countable came across Cantor's work, he found mathematical support for what he was doing theologically. So he got in touch with Cantor, and they both really appreciated each other. And Cantor came into correspondence with many Roman Catholic theologians and found a tremendous amount of affirmation and support there. In fact, take this next bit with a grain of salt. I'm not sure how to say it quite right. I've wondered, and I'm not the only one who's wondered, if Cantor may have actually converted to Roman Catholicism. There is no record of that. But one thing that he said in a letter, he had always wanted to teach at either Göttingen or Berlin because those were the top tier schools in mathematics. And he felt that he was being kept out of that from the people that were opposed to him. But at one point he wrote, "You know what, I'm actually glad that God didn't allow that to happen, because by staying here in Halle, I wasn't 100% focused on mathematics. I could do this work in theology, and in that way I could serve Christ and his Holy Roman Catholic Church better than had I had been able to if I had been exclusively preoccupied with mathematics." We also know that he met with a parish priest in Halle, and that they had private conversations. This may have occurred as he had attended Mass, or possibly not. We don't know for sure, and that may never be known. That's something that needs yet to be untangled. But yet, in letters that he wrote after this time, he would always emphasize very strongly that he was associated with the University of Halle, Wittenberg. Wittenberg, again, being the place where Luther had nailed the 95 Theses that started the Protestant Reformation. So Cantor, in the 1890s, there were some tremendous family difficulties. His mother died in 1896. His father had died about 30 years prior to that. His brother died in 1899. Also in 1899, he had his next breakdown. Now he had had a peace from that for 15 years. Okay, so 1884 was his first hospitalization. 1899 was the next hospitalization that's recorded. After he was out of the hospital, he was down in Leipzig. He was lecturing on Shakespeare and Francis Bacon, and word got to him that his youngest son, Rudolf, had died. And Rudolf was 12 years old. Rudolf was a very accomplished musician. He also played violin, as Cantor had. And by the time Cantor got to this point in his life, Cantor didn't even remember why he had loved mathematics so much, or why he had gone into mathematics and given up music. And he was kind of almost living his life through this son. So as horrific as it would be for any parent to lose a child, for Cantor to lose this youngest son, Rudolf, who shared so many of his interests and reminded him of himself, and through whom he was kind of reliving his youth, it was just an absolutely devastating blow. And after this point, Cantor ended up being hospitalized quite frequently, almost every other year, 1902, 1904, 1907, 1911, and it just kept coming. The university was very understanding of this and granted him leaves of absence for his teaching. So this was 1899 when his son died. Cantor did not retire until 1913, and he had to sometimes take leaves of absence because of his illness. Actually, during that illness in 1899, so kind of give you an idea of where his mind was at, he wrote a letter to the Ministry of Culture in Germany, and he said that he was absolutely serious about his feelings. He felt he was being persecuted, that people feared his research. He believed his work had serious worldwide significance. He had found information about the first king of Britain that would absolutely terrify the English. He was wary of his enemies who were keeping him silent because of secrets he might divulge. And he was asking the Ministry of Culture to allow him to abandon his professorship because he was determined to break away by all means. He asked if he could have a position, a quiet, modest position at a library instead, as long as he could keep his same salary. Okay, so that's a letter that he sent to the Ministry of Culture in Germany. However, and I am winding this up quite quickly here, towards the end of his life, he did get more affirmation from the mathematical community. In 1900 in Paris at the Sorbonne, there was an international congress of mathematicians that was held, and David Hilbert there presented a very unusual talk. Instead of talking about his research, he put forward what he felt were the 23 most important questions going into the new century, the 1900s. The top problem on his list was the continuum hypothesis. Number one problem that he felt was important for mathematicians to look at. Also, the British Royal Society awarded Cantor their Sylvester Medal, which is the highest honor that they can give a mathematician. Cantor was also invited to St. Andrews University for its 500th anniversary as a distinguished foreign scholar. And a year later, they awarded him an honorary doctorate. But then in 1917, he was hospitalized for a final time, and he really did not want to be there. He kept saying, he kept asking his wife to please bring him home. And this was in 1917, so this is during the time of World War I. There was not much food available in Germany. If you see pictures of Cantor from this time, you see that his cheeks are very hollow and he's quite gaunt. He's clearly malnourished. And he died in January of 1918 of a heart attack. So here is a picture of the tombstones, the family plot. And a little closer, we've got Georg Cantor and his wife Valley, and this is their son Rudolph and a daughter, Marie. But in a letter of sympathy to Cantor's wife, the mathematician Edmund Landau wrote, "Never will anyone remain more alive." And as I think about Cantor and his work, and I think about the triumph of his spirit over adversity and how he persevered in his work, even against all of those that were opposed to him, you know, to me, I do feel that he continues to live on. And his work is fundamental in mathematics. It's part of the standard core of an undergraduate degree in mathematics. And I just want to show you some of the honors, the plaques and so on. You've seen this already. Monument in Halle, a little closer look at that. There's a street in Halle that's named after him. This is his house, and there's a plaque that Cantor had lived there and what he did. On your way out of town, on the way to the train station, there's a pedestrian underpass, and they have posters there of some of the famous residents of Halle, and you see Cantor being recognized here. This is Manfred taking this picture for me. So I want to thank him again, and I need to give some more words of thanks. Again, thank you to Dr. Manfred Stern, Mrs. Petra Kühne, who helped me with the archival research regarding the church documents, and also Jacob Meyer, who put together my opening slide and helped me with some other digital issues and image issues. In case you're interested in looking into some of these other lives of mathematicians, I did keep a travel blog. The address is here, mathsab, for math sabbatical, mathsab.blogspot.com. That's a little harder to remember, but I'll just leave it up here. But this is the talk that I gave on women in the 19th century and the obstacles they had to overcome. So I went a little over time. Thank you so much for your patience. Appreciate you coming out on this Friday night.